Hey there, guys. It is Monday the 26th. We're going to look at Chapter 8 for our AP Chemistry class today. Here's our assignments. We've got Chapter 7 quiz, which is due today. This is the quiz over atomic structure that I gave you guys. I did an example in a video that I sent you. Make sure you watch that video. Each of you guys were assigned an element and then asked to answer questions about the element. Just do the best you can. I'm not going to grade it too hard. There are some... Because each of you guys has a different example, different element, there's kind of a difference in difficulty for certain questions. Certain questions are significantly difficult to answer, and we can kind of just predict the best. So if you want to just provide a prediction, I'll give you credit for that, and that'd be fine. Now there are some questions that are, there's going to be a right and wrong answer, and you guys should get those. Number of protons, number of electrons, average atomic mass, that kind of stuff. So that should be fine. Exit ticket from Monday the 19th. I don't know if I got any of these, maybe a few. And I got a couple of the Chapter 7 quizzes, but not many. I think I got 2 of them. And then the exit ticket was like 5 questions, maybe 10 questions. Pretty easy over atomic structure and PES diagrams. Make sure you watch that video on PES diagrams. It's very helpful. And then we have Chapter 7 NIMSY notes that are past due. Those were due last Friday, I believe. Some new assignments. We've got the Chapter 7 AP multiple choice questions, which I like to think of it as kind of a assessment over this chapter. Since we won't have time for a formal exam, I kind of think of this as kind of a quiz over that chapter to kind of check yourself and see if you're getting the chapter, and maybe you can go back and see what we missed, see what are we not getting, and what do we got down. That way we know what we need to brush up on. And then Chapter 8 NIMSY notes. Chapter 8's on bonding, so we're going to start that chapter today. I'm going to make it due next Monday. That way you have time, and you guys can complete the NIMSY notes kind of as we complete this chapter. We're not going to spend too much time on this chapter, however, and I do recommend doing the NIMSY notes for all of the chapters, and I'm going to make it a grade for each of them. We still have Chapter 9, 10, and 11, so we still have 3 chapters. They're pretty short, though, especially Chapter 9. Most of Chapter 9 is actually beyond the scope of AP Chemistry, so there's not a whole lot in Chapter 9, although what we do have to cover is very abstract, but it's not too bad. And then 9 and 10 are pretty short chapters. So we're almost done here. Can you guys believe it's the last week of April? So this Friday is the 30th, and so we'll be testing, AP testing here soon. Let's see, today is Monday. Not this Friday, but next Friday is y'all's AP test. So it'll be nice to kind of get it out of the way. And then once we're done with the AP test, we've got a few things that we'll do, but really not much. So there is light at the end of the tunnel. We're almost done here. And I applaud you guys for sticking with me and working as much as you can to kind of learn these concepts and practice these skills. And these skills that you're learning in this class, especially the math and problem solving, will take you, and it'll be with you anywhere you go. So I definitely applaud you guys for taking an advanced course and learning what you can and practicing these skills. Okay, let's see. So here's our calendar. Today we're going to talk about bonding, mainly going to focus on polarity and Lewis dot diagrams. Not really too advanced stuff, exceptions to the octet rule. And then Wednesday we're going to do the other half of this chapter, which is on the Vesper theory, which talks about predicting the shapes of molecules, which is really cool. So you guys will like that one. And we'll do a virtual lab with this. Actually, I have some virtual labs with polarity as well. Maybe we could do that. Maybe we won't have time to do it in class, but I can give you guys the link, and I can encourage you to look at those virtual simulations and play with it, and that way you can kind of engage with the material, and that way get your hands dirty and get an idea of how this chapter will work. Especially polarity. Polarity is difficult, but you guys will get it just fine. And then Wednesday we will probably start chapter 9 as well. I'd like to start introducing the hybridization model for atoms. And then Friday we will kind of continue and finish chapter 9. Let's see. So here's our schedule up until the AP test. So chapter 8 this week. We'll start chapter 9. We'll finish chapter 9 on Friday. And I'll be making a video, and if I can't cover everything in the video for you guys to watch during class, then maybe there'll be a little bit of the video that you guys will have to watch outside of class. But I just want to make sure that we get the chapters covered. I don't want to cover chapter 9 for a week, which is what we kind of need, but I want to cover it in 2 days, and that way we can continue and get to chapter 10 next Monday, and then next Wednesday we'll do chapter 11. And again, if you guys want to review for the AP test, I encourage you to work on some review materials over the first couple of chapters: stoichiometry, kinetics, equilibrium, just to make sure that we are working on the skills and we're ready. Next Friday, not this Friday, but next Friday is our AP test. All right, so let's draw the Lewis dot diagrams for the following elements. You guys are going to complete a Nearpod, so let me show you how this Nearpod is going to work if you have not done one before. I'm sure you guys have done a Nearpod, but if not, check out how to do a Nearpod. Let me open it. So I'll give you guys a link in the chat. It's going to look like this. Oh, let me leave student view. Maybe I can't do student view. So it'll look kind of like this. It won't be the same, but it'll look kind of like this. There we go. You're going to say, put your name there, join the lesson, and then there's going to be slides like this one where there's really nothing to do. It's just the PowerPoints that I'm going through in class, and so just kind of click through until you get to the warm-up. And then, okay, here is the warm-up. Notice that the two sides of the slide are black, and there's a toolbar down here. So these are draw it slides, and what I need you guys to do is to draw the Lewis diagrams for these elements. Okay, and I'll be doing the same. So there's a slide for each of these in the warm-up, and then we've also got some notes that we'll do. So let me show you that. So that's our 5 questions on the warm-up, and then here's some more notes, and then there's an activity to do. So I need y'all to write on that slide. You can draw. The default color is brown, which I don't like, so I recommend changing the color. You can also change the size of the pen. This is a highlighter here, I believe. Yep, that's a highlighter. This is text box, so if you want to type your answers, that's probably the best way to do it, especially if you have a long response. You can upload a picture of your work. You can erase. This will erase things like an eraser. And then this will delete everything on the slide. This will lock the slide so that you can't write on it anymore. And most importantly, after you're done working on a slide, make sure you hit submit. So write your answer and then click submit, and it'll save it. It saves it one slide at a time automatically into Canvas. All right, this slide is that's the answers right there actually for that one. All right. And then here's a slide, notes on metallic bonding. And then we've got lots of notes here that we'll go through. Just fast forward through them. Maybe I should have taken them out of the Nearpod. And then there's the next one to work on. Draw the crystal lattice structure for sodium chloride. Draw some Lewis dot diagrams that we'll do, and so on. Just make sure you go to the end of this presentation. Let me show you what the last slide is that I want y'all to do. That's the end of the Nearpod there, slide 38. And the last one that y'all need to complete is slide 36, polar versus non-polar covalent compounds. So we're going to determine whether each of these molecules is polar or non-polar. That's a little tricky to do, so we'll do that. All right, so make sure you guys submit it. Again, make sure you click that submit button after each slide, and it'll automatically save it. Okay, so let's draw the Lewis dot diagrams for the following elements. How do we draw Lewis dot diagrams? Well, these are Lewis dot diagrams or Lewis structures for elements, which means that we're going to draw the symbol for each element. Let's go ahead and do that. I'm going to kind of spread them out so I got some room for each one. There we go. We're going to write the symbol for the element. Let's connect that. There we go. And then we're going to put dots on each of these to indicate the number of valence electrons. So a Lewis dot diagram is simply a symbol for the element and then a dot for each of the valence electrons up till 8. So all of these elements will have anywhere from 1 to 8 electrons around it. And that's going to be based on the location of that element on the periodic table. So hydrogen is in group 1, so he will have 1 valence electron. So I'm going to put 1 valence electron on him. And I'm just going to change the color so that you can see it better. Helium is in group 2, so he will have 2. Remember that group 8, the noble gases, don't react with anything. They're noble and they're inert gases. Most of them have 8 valence electrons. They have full outer shells. Helium only has 2, and it's because helium is in the 1s, and it's the first shell only holds 2 electrons. So helium is in group 8, but you got to remember that he only has 2 valence electrons. Right? His atomic number is 2. So he's got 2 protons, 2 electrons if he's neutral. All right, lithium is in group 1. All right. Now lithium has 3 protons and 3 electrons. So if we draw a picture of lithium up here, he's got the 1s, there's his nucleus in the middle. The first shell is the 1s, and there's 2 electrons in there. And then the second shell is called the 2s, and there's 1 electron. So we're only looking at that 2s. And so that dot there is that electron that's in the 2s shell. We're not going to draw the dots for all of the other electrons because they're inner core electrons, and essentially they don't react with anything. So when lithium goes to react, this outer shell electron is the only one going to be involved and playing that reaction game when it's going to react with other elements. Magnesium, is in group 2, so he will have 2 valence electrons. Even though magnesium has 12 electrons, that outer shell is going to have 2. Oxygen is in group 6, so he will have 6 valence electrons. 1, 2, 3, 4, 5, 6. Carbon is in group 4, so he'll have 4. Fluorine is in group 7, so he'll have 7. And if you guys notice how I'm writing these, I'm starting on the right side. So the rule for writing Lewis dot diagrams is you start on the right side. So if you got your symbol here, you're going to start here, put a single dot, and then work your way counterclockwise around the atom, putting a dot on each corner, if you will, north, south, east, west, and then pair them up after. And that's how you should do them, and that's how they'll appear when they're done correctly. So there's our Lewis dot diagrams for the following elements. Easy peasy. Alright, next slide. Arrange the following ions by decreasing ionic size. Okay. We have... This kind of goes back to chapter 7. Although chapter 8 actually covers ionic size. I hit ionic size back in chapter 7 because we talked about all the trends, but really in the book that I have, ionic radius, ionic size is in chapter 8. So let's go through this. What has the largest negative charge? The largest negative charge will be the largest, so that's the largest. Because the more electrons you gain, the more they're going to repel each other, and it's going to blow up the size of that atom, or the size of that ion. And then the most positive charge will be the smallest. So that's our smallest. And then we know that anions, or negative, will be larger than cations, or positive. So the anions will be larger. So the largest one, we're going to order this in decreasing size. Alright, which means we're going to start with the largest and work to the smallest. You have to read these questions carefully, guys. Because if you're answering a question like this and you're doing multiple choice, it's easy to do it backwards. So it says by decreasing size. So you got to understand that it's the largest and then all the way to the smallest. So we're going to start with selenium. And notice that I ordered these based on their charges. I don't have to look at the periodic table and see where they're at all. I'm just doing this based on charges. Now, if we had two ions that had the same charge, like these two, none of them have the same charge here. If we were going to compare a bromine ion, a -1, to a chlorine ion, well, then we would look on the periodic table and say, okay, the ions get larger as you go down, and they get larger as you go to the left. So then you can compare their sizes. But since these guys don't have the same charge, we can't really do it that way. So we're not even going to look on the periodic table to see where they're located. We're just going to look at their charges. We know that the selenium is going to be the largest because it's gaining 2 electrons to become a -2. And those electrons are going to repel each other and make the atom bigger compared to how big it was as an atom. All right, and then and it is significant. It's going to significantly increase the size of the atom, more so than looking at the periodic table and seeing where selenium is compared to these other elements. That's going to make it bigger regardless of what those other elements are. Almost, most of the time. Okay, 99% of the time. There's going to be exceptions to that, but 99% of the time. The next one is going to be our anion, which is going to be bromine. He's going to be larger because he's got a negative charge, so he gains an electron, making all of the electrons uncomfortable and repelling each other, and so they're going to spread out a little bit and make a larger atom. The next one is going to be the rubidium with the +1, and then the most positive charge will be the largest, because you're losing 2 electrons, and when you lose electrons, you're kind of essentially deleting a shell and making an atom smaller. So there's our sizes, so I wanted to practice that. Excuse me. And I'm interested to see if you guys get the same thing I got. All right. Number 3. Choose the ion with the largest ionic radius in each of the following. So we have A and B. So for A, we want to look at these guys and determine which one is the largest. If you look on the periodic table, here's their order on the periodic table. We have hydrogen, lithium, sodium, potassium, rubidium, and cesium. I almost needed a periodic table to put those in order, but surprisingly I didn't. So as you go down, they get larger. Smaller up here. And the reason they get larger, as you guys know, is because there's more shielding. So the nucleus has less effective nuclear charge, which means that the positive charge in the nucleus is less effective at holding those electrons. So those electrons are free to roam a little bit and get a little bit away from the nucleus, making the atoms larger. Also, you have more and more shells, and if you draw an atom with many shells, it's larger than an atom with less shells. So that's obviously going to be more larger. So cesium here is the largest. All right, so you can circle your answer or you can write it. Either way is fine. And then we're going to circle the largest one here. The largest one is going to be the most negative charge. So the largest will be tellurium. Let's put these in order. Tellurium with a -2 is going to be larger than the iodine with a minus. Iodine's a huge atom, by the way. 127 electrons. That's a big boy. A lot of electrons. Cesium is going to be smaller, and then barium is going to be the smallest. So if you want to put them in order, that's how you. This question's only asking for the largest, but I wanted to go ahead and put them in order. So tellurium will be the largest. Awesome. All right. Next slide. What are the 3 main types of bonding? Describe them briefly. So if you guys should be able to do this, but I'm gonna go ahead and go over it. So we have ionic, we have covalent, and metallic. An ionic bond essentially is between a metal and a nonmetal. Covalent is 2 nonmetals, and a metallic is going to be metal ions. Okay. Ionic is going to be where electrons are transferred. Covalent is where electrons are going to be shared. The only thing we can really write for metallic is C of electrons, and we'll talk about that. Basically, if you have an aluminum metal, it's aluminum ions and a sea of electrons, all kind of attracted to that positive charge. They're all negative, and so it's just a aluminum, and then over here there's another aluminum ion, and it's held together by electrons as well. So that's kind of metallic bonding. Ionic bonding, we're going to change the ending to "ide." Ionic compounds are weaker than covalent bonds. There's a lot more details with them. They usually are, the ions themselves will conduct electricity. The solid salt won't. So they conduct electricity when they're ionized. Covalent compounds are going to have IDE as the ending, but we're going to use prefixes like carbon dioxide. So we're going to use prefixes in naming them. These are usually stronger. These are usually gases, often, but not always. These are going to be stronger. These are going to be, they're not going to conduct electricity. They're going to be insulators instead. So they're going to protect and prevent the conduction of heat and electricity. So they're going to be insulators. That's pretty much it. They're going to share electrons. An example of ionic compound would be sodium chloride, NaCl. An example of a covalent compound would be water. And then an example of metallic compound would be like any pure metal, like copper, like pure elemental copper, Cu. I can't write a U there for some reason. There we go. Copper, silver, gold, platinum. Those are like metallic compounds with pure metals with no oxygen or anything else. All right, next slide. Calculate the delta H from bond energies given in the table for the following reaction. And again, this is messing up. I've got my arrow there. There we go. Alright, so we're going to look on this table. We're going to write that for this reaction. These are all gases, so you have to look at the state of matter. And I'm going to go ahead and circle the numbers that we need. We need CH4, so we have 4 CH bonds. So when you do bond energies, you're going to take the bonds, so the delta H for reaction is going to be bonds broken, the sum of the bonds broken minus the bonds formed. Alright, so it's almost kind of like reactants minus products. So it's a little different than what we were doing for delta H when we had the delta H for each substance. So in this case, we're looking at the bonds. So we have 4 CH bonds. So single bond CH, where's that? There it is. We're going to do 4 times that. So 4 times 413. We have 2 Cl2s. That's supposed to be a lowercase Cl. So 2 chlorines. Cl-Cl bond, which is a single bond. There it is. We're going to have 2 of those. So 2 times 239. I think that says 239. Yeah, 2 times 239. There we go. 2 fluorines. FF. Where are you? There we go. 154. So 2 times 154. And so we're going to add all that up. Okay. So 4 times 413. Let me get my calculator. Do I have this one done on paper? I should. I don't have it very neat though. I didn't show all my work, so let's show my work. So 4 times 413. That's 1652. Why is my pen messing up? 1652 for the CH's. So let me circle it after I get it done. Then we're going to do 2 times 239. That's 478. And then 2 times the fluorine, which is 154. That's 308. We add all this up. 1652 plus 478 plus 308. So that's 2438 kilojoules. So that's the bonds broken. And we're going to subtract that minus the bonds formed. Alright, so we have that number. Let me write that number down. 2438. Okay. And then let's do the bonds formed. Bonds formed is going to be CF2Cl2. If we draw the Lewis structure for that, which we'll talk about later, we're going to have 2 chlorines attached to that carbon, and then 2 fluorines attached to this carbon. Actually, no. This is what it looks like. Let me redraw that. CF, Cl, Cl. The arrangement doesn't really matter. The fact is, there's 1 carbon, 2 fluorines, and 2 chlorines, and so 2 of these arms are fluorine arms, and 2 of them are chlorine. So we have a carbon-chlorine bond. There's 2 of them. So let's find that one. Carbon-chlorine is right here. There's 2 of those. So that's 2 times, I can't read that, 339. 2, so 339. And then we have 2 fluorine bonds right here. So that's going to be 2 times 485. So that'll cover this compound. Then we have 2HF, so that's 2 bonds of HF, so that you're going to have to do the moles here. Wait, did we do the moles? Bonds broken? I don't think so. I think we just added up, but let me see what we get. I don't remember if we need to do... guess I need to look in the book. Let me get my book. I don't remember if we need to use the coefficients or not, because the number I got a second ago, 2438, for the bonds broken, was not including these coefficients. So let's see here. Chapter 8. Let's see where this one's at. Bond enthalpies. Maybe this is in chapter 8? Chapter 7? Oh, here we go. So 4 of those, 2 of those. I guess we did use them. Okay, so we're going to need them. Okay, so you do need the subscripts. I'm sorry, the coefficients. So if we have 2HF, we're going to do 2 times the bond of HF. So the HF is, excuse me, HF, where are you? Here's HF, 2 times 565. And then 2 times HCl, 2 times 427. Okay, let's add all that up and see what our bonds broken is. 2 times 339 plus 2 times 485 plus 2 times 565 plus 2 times 427. Woo, 3632. Okay, so we're going to do broken minus formed. Our broken was 2438. We're going to minus 3632. We're going to get a negative number, and it's negative 1194. Negative 11. My pen is not working. It's driving me nuts. 1194 kilojoules. And that is our delta H. So you have to look at how many of that bond is in that compound. So for CH4, we did 4 CH bonds, right? And if you need to draw them out, draw them out. CH, 4 CH bonds, right? Oh, and I forgot to mention, guys, if you look at the slides when you're doing these, every slide that you need to complete has a star with a smiley face on it. So that tells you which slides you need to do. The star with the smiley face on the top left. I forgot to mention that. So we have CH4, which is, if you draw the structure of that, CH4, it looks like this, and we'll do Lewis structures in the notes today. So CH4, so there's 4 of those CH bonds. Right, so that's why we multiplied by 4. Now, if we also had a coefficient here, let me erase. So if we had a coefficient here, we would also multiply that coefficient by 4. So if we had 2 of them, we would do 2 times 4. We would have 8 of those CH bonds. All right, so you got to multiply the coefficient by the number of bonds. We had Cl2, which a Cl2 molecule looks like this. Cl, Cl. So 1 of each attached. You get 2 of them. So we have 2 of those, and we did the bond energy of that times 2. We had the fluorine. We had 2 of them. This one we only had 1. This one we had 2. This one 2. So you got to watch the coefficients here. All right, wasn't that fun? Combining good old thermodynamics with bonding to figure out the enthalpy of a given reaction. That's kind of cool. All right, that's it for the warm-up, I think. I could be wrong. Let me close this. All right, that is it for the warm-up. Okay, so let's talk about ionic bonding. Ionic bonding is where electrons are transferred between atoms. We need a metal and a non-metal. Atoms are going to be held together by electrostatic attraction according to Coulomb's law. Coulomb's law essentially looks like this. It says that the energy is equal to some constant And usually that constant is not needed. I think if you look in our AP Chemistry formula sheet, that value might be in there. And actually, let me look real quick. Just make sure we dot all our I's and cross all our T's. Let me have a look real quick and see if it's in there. AP formula sheet. Atomic structure. There's not even a section about atomic structure, is there? Oh, it might be in electrochemistry. No, I'm not seeing it in here. I don't think the constant value is important. We have the charge of an electron, we have Avogadro's number, the speed of light, and Planck's constant. So I don't think we're going to need it. But if you needed it, they would give it to you in the problem. So it's something times something raised to the power of like -19, something like that. And it's just a constant to make the equation work. Q1 and 2 are the charges. So Q is the charge. So if it's an ion with a +1, then Q is equal to +1. If the charge is equal to +2, then Q is equal to +2. So you keep the charge there, and you keep the sign. And then R is the distance, the ionic radius. So essentially, if you have two atoms, like so, and there's their nucleuses, R is essentially that distance between them, which is proportional to their both of the ions' atomic size or ionic size. Okay. The larger the charge, so if the charge goes up, then the energy goes up. More charge means more force of electrostatic attraction. So opposite charges attract. The more charge you have, the more energy, the more force you have holding them together. We can also call this lattice energy here. So let's write that. So lattice energy. L-A-T-T-I-C-E, lattice energy, which makes me think of lettuce. Lattice energy is the energy that holds an ionic compound together. But it's also force, so this could also be the force between ions, the electrostatic force holding them together. As the distance goes up, as the ionic size goes up, energy goes down. So that's the relationship you all need to understand with Coulomb's law. If the charges of the ions are more, then the force holding them together will be more, and it'll be a stronger compound. Stronger forces holding those ions together. More lattice energy, which we'll talk about in a second. The ionic size, if it increases, then the energy decreases because it's in the denominator. All right, the smaller the distance between them, the smaller the ionic size or ionic radius, the stronger the energy. So if the ionic size goes down, then the energy will go up. Okay. And I kind of relate Coulomb's law with gravitational law of attraction, Newton's law of gravity, which says that gravity is equal to some constant times the mass of one object times the mass of the other divided by the square of the distance. So it's a very similar equation. And the way that I relate it is I just know that, like this one, if Q gets larger, then you have more energy, right? Well, just like gravity. If you have two larger objects, if the mass of the object gets larger, then we know that the gravity gets larger, or the energy between the two objects gets larger. And then the force gets smaller the farther they are apart. So the sun is a good distance away from us, 97 million miles or something like that. And so we divide by that distance to get the force of gravity from the sun to the earth. And then, of course, the sun's a lot larger, so it's more massive, and so that's more gravity. So I like to relate these two together because they're very similar. Okay. All right, I think we have an example to do here. Which bond is more ionic, has a stronger electrostatic force? So So we can use Coulomb's law, this relationship here, some constant times the charges, the product of the charges, divided by the ionic size. We can use this to determine which bond is more ionic. When it's more ionic, that means it's stronger. And we can compare the strength of these bonds, okay? So sodium chloride versus magnesium chloride. And let me look at my notes here. Oh, 35 minutes. This is going to be a long video. Let's see how we do. Let's look at sodium chloride. So sodium chloride is NaCl, and sodium's a +1. If we look at magnesium, magnesium's a +2 because it's in group 2. So magnesium is, so this one is larger because it's less positive. This one's smaller. So smaller ionic radius, larger ionic radius for the sodium, and smaller ionic radius for magnesium. And then if you look at the distance, so if let's set up the Coulomb's law for each of these, just looking at the distance. So we can already tell that magnesium is probably going to be smaller because of its charge. So let's look at, so the force for sodium chloride is going to be equal to K, which I'm not even going to write because it's going to be the same for both, so it doesn't matter. Q1 is going to be +1, sodium's a +1, and then that chlorine is going to be a -1. And then the distance between them will be larger, so we're going to put larger. Okay? So we have a small charge divided by a larger size. All right, let's look at the force for magnesium chloride. We're going to have a +2 here and a -1 there. So we have more charge on top, and we have a smaller on the bottom. So if we compare the numerator for these two, +1, this one's got a +2, so this one's larger, just based on that charge, right? Magnesium has a +2 charge, whereas sodium has a +1. So this numerator is going to be larger. And then we are dividing by a number up here that's larger, which means it's going to get smaller. So F's going to get smaller the larger that gets. And then down here we got smaller, so that means that the force is going to get larger. So that tells me that the force of MgCl2 is greater than the force of NaCl. So so magnesium chloride is going to be more ionic. It's going to have a stronger force. All right, so using Coulomb's law, we should be able to do that. We should be able to compare the ionic character of many different ions and different ionic compounds, and we'll do that in Chapter 10. So we'll revisit this in Chapter 10. This is kind of just an intro to Coulomb's law. All right, so magnesium chloride is a stronger, more ionic compound. It has a more ionic character because its bonds are stronger. Okay. Cool. I think I got a little bit more with ionic compounds here. So here's an answer key, basically the same thing we just wrote, so you guys can read through that. I wanted to include that so that it's there, just a good description of that. Metallic bonding is bonding from the electrostatic attractive forces between delocalized electrons. Delocalized electrons are electrons that do not belong to any one atom or another. So if you have a sample or some kind of a substance, these delocalized electrons are just randomly distributed electrons that don't belong to one atom. They're not really attracted to a particular nucleus, okay? So they're delocalized free electrons, and the positively charged metal ions or cations. So these are all for metals, so one metal atom that gets a charge, and it's going to be attracted to these free roaming delocalized electrons. So these metal cations are said to be in a sea of delocalized electrons. Metallic bonding is the sharing of free electrons among a structure of positively charged cations. Metallic bonding accounts for many physical properties of metals, such as their strength, ductility, thermal and electrical conductivity, opacity, and luster, shininess. Here's some examples of metallic bonding. So pure gold, pure silver, pure platinum, and pure copper. They will have this kind of bonding model. Metallic bonding, sea of electrons. So that's a picture of it. So you might you might be asked to draw a picture like that on the AP test. Not likely, but it's possible. Okay. So that's just a little quick overview of metallic bonding. Let's look at ionic. Okay, so ionic compounds are going to be formed by ions when an element gives or takes electrons. A metal and a nonmetal is going to make an ionic compound. Valence electrons will be exchanged or transferred. Sodium chloride is an example. These are weaker than covalent bonds. We're going to name them by changing the second element to IDE, so NaCl, sodium chloride. All right, let's look at some examples here. So Kf, potassium fluoride. So there's the metal atom. So potassium is in group 1, so it's got 1 valence electron. Here's fluorine. He's in group 7, so he's got 7. What's going to happen? Potassium is looking to get rid of his valence electrons to empty his valence shell so that the more inner electron shell is going to be full, right? Because all shells before this outermost shell are going to be full. So if you get rid of that outer shell, now he has a full shell. And that's what metals will do. They're going to delete their outermost shell in order to have a full outer shell, which is now closer to the nucleus. And then fluorine has 7 valence electrons. He's going to pull on that electron. He's extremely electronegative, which means he's going to pull that electron. So he's going to go ahead and pull it. Oh, and it doesn't do it, but you should see I actually had an animation here where the electron will move over here. And so this is what it's going to look like. Potassium is going to be naked. No electrons around him. He's +1 charge. Fluorine is going to be full, 8 valence electrons. And that's what we're going to see in every single ionic example. So let me go through. Also, we got the charges, plus on the metal, minus on the nonmetal. So this is a good review. So let's go ahead and look at these. This one, there's 2 metals, and they're both going to give away an electron, so that oxygen, which has 6 valence electrons, will gain 2 to make 8. So we can have that happen. We can have calcium chloride, which is 2 chlorines are going to each take 1 of calcium's electrons. And then sodium nitride is where we're going to have 1 nitrogen that has 5 valence electrons, and he's electronegative, so he's going to pull electrons from 3 sodium atoms, which is cool. So there's some examples for ionic. And then here's covalent. Covalent, we're sharing electrons. Only nonmetals are involved. Valence electrons are shared, which means that they belong and are owned by both atoms. Okay. So H2 is an example. These are strong bonds. We use the prefixes for naming these. Mono, di, tri, tetra, penta, and so on. Here's some examples of these. So here's chlorine. I don't know if you guys can see these dots here. Let me actually draw on top of this. I don't know why it's white. It's actually not supposed to be white. So chlorine has 7 electrons. Here's another chlorine atom, his twin. They're going to meet up, and basically they're going to say, hey, if we both share these 2 electrons, then we both have 8. And so that's what's going to happen. So chlorine is going to share those 2. We can actually circle them, and then we can have the remaining 6. So if you look at this chlorine atom, he's got 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. And then let's look at this guy. 1, 2, 3, 4, 5, 6, 7, 8. So if they both have 7 and they need 1, if they share an electron, then they make a bond between them. This is called a covalent bond. And they both now have 8 valence electrons. There's 2 ways that we can draw this. We can draw it to where there's 2 dots in between them. And we actually don't need that circle around it, but I like to circle them. But let's get rid of this circle here. If I can. My pen will work with me. There we go. So you can put 2 dots between them, and when you put 2 dots between 2 elements, it means that they're shared between them. Or you can put a line, and we got to understand that these bonds are between 2 electrons. So there's an electron shared between those atoms, and that's why we show a line between them. So we're going to use dots for lone pair electrons and lines for bonds, and that's the most useful and common way to show covalent bonding in Lewis dot diagrams for covalent compounds. All right, so there's chlorine. Even though it's hard to see, let's click through it. All right, let's look at CO2. CO2 is interesting. I'm just going to do this one by hand. So carbon, first we can start by drawing the Lewis dot diagram for each of the elements in the compound. We have carbon, which has 4, and we have oxygen. We have 2 of them, which has 6, so 2 oxygens. So what's going to happen is, let's try to make a bond between these two. And then let's show the valence electrons. So there's 2 in that bond there. 1, 2, 3, 4, 5. So if oxygen has 6 valence electrons, when he bonds with carbon, he's going to have 5 over here. 1, 2, 3, 4, 5. And then that's a 6th one that he's going to share with carbon. Carbon has 4. 1, 2, 3, 4. And of course the 4th one is going to be shared. If we go ahead and circle each of these elements, let's count. How many electrons does carbon have after making a single bond with oxygen? 1, 2, 3, 4, 5. That doesn't work. He needs 8. All right, he needs 8 valence electrons to be happy. So carbon's not happy with a single bond. Let's go and look at oxygen. Oxygen here, 1, 2, 3, 4, 5, 6, 7. 7 electrons, not happy also. That kind of looks like a donut, doesn't it? And that last drawing I had looked kind of like a smiley face. So it's kind of funny. So neither of them have an octet. So what do we do when we use up all of our valence electrons and we cannot make an octet between the atoms? What we do is we go for a double bond. So let's go ahead and show you how to calculate the valence electrons. Carbon is in group 4, so he's going to have 4. And then oxygen is in group 6, but we have 2 of them. So 6 times 2. So that's 12. So 12 plus 4, we are only allowed 16 electrons here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh wait, we're not drawing the other oxygen. Let's draw the other oxygen. So let's put carbon in the middle, and we're going to draw a bond between them. And remember that bond is going to be 2 electrons shared between them. So I forgot to draw the other oxygen. So let's try this again. Carbon has 4 electrons. 2 of them are going to be shared with that oxygen, and he's going to have 2 left. Oxygen is each going to have 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let's try this again. Let's see if a single bond will work. This oxygen has 1, 2, 3, 4, 5, 6. He's not happy. This carbon has 1, 2, 3, 4, 5, 6. He's not happy. And this one's not happy either. So how can we make all of these happy without using more than 16 electrons? We have, how many electrons do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Am I missing something? 1, 2, 3. Maybe I'm missing something. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I think I was missing one. There we go. All right, so let's try this again. Sorry, guys. Let's do a count. 1, 2, 3, 4, 5, 6, 7. He's 1 short. 1, 2, 3, 4, 5, 6. He's 2 short, so he's not happy. 1, 2, 3, 4, 5, 6, 7. So nobody has an octet, and we're using 16 electrons. Okay, let's count our electrons. Make sure I'm doing this correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. So we got 16 electrons. So let's show what's going to happen here. Let's try this again. Carbon is actually going to form a double bond with both of these oxygens. So if you try to make an octet, remember we only got 16 valence electrons. Carbon's got 4 of his own, and oxygen's going to have 6 of his own. So, and we got 2 of those oxygens lying around. 2 oxygens. Only 16 valence electrons. A single bond's not going to cut it. What's going to have to happen is each of the oxygens is going to donate another electron to form a double bond, to form another bond with that carbon. And both oxygens have to do it for this to work. So let's see what happens here. So carbon has 4 valence electrons. If we have a double bond on both sides, all 4 of those electrons are used up in those bonds. Oxygen has 5, so that means that 2 are going to be used up in the bonding, and then 3, 4, 5, and 3, 4, 5. So let's go ahead and check. Do we have 16 electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's see, 1, 2, 3, 4, 5. We're going to need one that's going to be a double because we need to have 6 electrons on oxygen. So let's change them. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then you can see that carbon has the 4 red. So that's the all the electrons there. We have 16 electrons. Let's check our octet. Let's look at this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. So counting the 4 that are shared with the 6 of his own, or 1, 2, 3, 4, 5, 6, 6 of his own, counting the 2 from carbon. So counting the 2 from carbon, we have 6 of his own and 2 from carbon in red that you see there. That gives us 8, and we're happy. Let's look at this one. Same thing, 8, and we're happy. Now let's look at carbon here. 8. He's got 2 of his own on this side, 2 shared with oxygen, 2 over here red that is on his own, 2 shared with oxygen. That's a total of 8 electrons. 4 on each side, right? So that's our Lewis structure for CO2. And that's how it looks like. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 on this side, 8 on this side. So that's our Lewis dot structure for CO2. So if you can't make an octet with single bonds, go to double bonds. Oxygen likes to make double bonds, but it doesn't have to. All right, so don't assume double bonds unless you try it and find out that it can't make an octet without it. What's next? Water. All right, so let's do the Lewis structure for water. You guys know this one, so I'll just do it real quick. So hydrogen has 1 valence electron, oxygen has 6, and there's 2 of them. So we're going to put oxygen in the middle. We're going to make single bonds. Each that oxygen is going to have 4 left over. H2O, so that's 2 from hydrogen, 6 from oxygen, so that's total 8 electrons. Let's check and make sure we got 8 electrons in our picture. That's 1, 2, 3, 4, 5, 6, 7, 8. There we go. Let's check our octet. Octet on oxygen is happy. 1, 2, 3, 4, 5, 6, 7, 8. So he's happy. Let's check the hydrogens. Hydrogen needs a duet. And there it is. So 2 electrons in each hydrogen. Remember, hydrogen is in group 1, and he's only got the 1s, and so he just needs to fill his 1s shell. So his max is 2. So there's the Lewis structure for water. H, O, H, and then 2 lone pairs. All right, what else we got? Oops. Okay. CH4. There's a Lewis structure for that one. It's going to be basically a carbon center and then a bond for each of those 4 hydrogens. So it'll look kind of like this. So 4 hydrogen arms, like that. Okay. And carbon kind of makes a backbone, and so that's why carbon is used in biological systems and used to make up a lot of compounds, is because it makes a backbone and it can make structures. There's oxygen, which we've done. Oh, have we done oxygen? Let's do oxygen. Oxygen is O2. So we have 2 oxygens, 6 valence electrons for each, so that's 12 valence electrons. So let's go ahead and connect them. I'm going to go ahead and do a double bond just because I know that they're a double bond. And then there's our Lewis dot diagram for oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 valence electrons. If we count our octets, we have 8 around that one and 8 around that one. And you have to include the 4 in the middle to both. The 4 electrons shared between them belong to both of them equally. All right? And I like to draw a Lewis dot diagram cartoon here. There we go. There's oxygen as a cartoon. Okay, let's see. Ionic bonding. Here's some examples of ionic bonding, but I'm not going to go through it, so you guys can go through that. It's the same examples as we've looked at before. Very similar. Sharing transferring electrons, making the nonmetals have an octet, and then completely emptying the valence shell of the metals. Here's some more covalent bonding. Let's look at these and then let's draw them. So H2 looks like this. Two hydrogens attached with a single bond with 2 electrons shared between them. Remember, hydrogen's max is 2. Here's a fluorine. They both have 7 of their own, and they share 1, and that gives them 8. And then oxygen is that double bond with the 2 on each. All right. What else we got? Nitrogen, CO2. We did water, so let's look at the nitrogen. Nitrogen's interesting. So N2. N2, that's 2 times the valence number of nitrogen, which is 5. So we have 10 valence electrons to work with. If we do a single bond, 1, 2, so it's 1, 2, 3, 4, 5. So if we did a single bond, counting the 2 in the middle, let's look at this one. 1, 2, 3, 4, 5, 6. Not going to do it. Not going to do it either. 1, 2, 3, 4, 5, 6. So they both only have 6. All right, let's make a double bond. If a single bond ain't going to work, fine. We'll do a double bond. If we do a double bond, we have to, what's going to happen is actually one of those electrons is going to be donated to the center. So both of these guys got to go. They move to the center. All right, let's check it. We still have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's check this one. 1, 2, 3, 4, 5, 6, 7. Not happy. And 1, 2, 3, 4, 5, 6, 7. That's an electron up there. Not happy. Okay, so a double bond's not going to cut it. Let's try a triple bond. Jeez, what does it take for this nitrogen? He's awfully needy. We're going to have to erase another electron from both of them and move it to the center. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We still only have 10 electrons. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Finally. And then this one's going to have 8 as well. So that's what we're going to need. We're going to need a triple bond. So N2 is N, triple bond N, and there's 2 electrons left over on both. All right, and so there's some patterns here. If you have a single bond, especially like oxygen with a single bond will have 6 electrons left over. A double bond for oxygen is going to have 4 left over. A triple bond, although oxygen doesn't really do triple bonds, so let's not even worry about it. Let's do nitrogen. If nitrogen has a triple bond, he's going to have a pair left over. So that's kind of what they usually look like. Hydrogen cannot do double or triple bonds. Hydrogen only has 1 electron to share, and once he shares it, his electron's full. His shell is full with 2, so he cannot do double bonds. Oxygen can do it. Nitrogen can do it. Sulfur can do it. We could easily replace this with sulfur because sulfur's in the same group, so we could easily replace that with sulfur. We could easily replace the nitrogen with phosphorus, and it would do the same thing. So just some ideas there. All right, so let's draw some Lewis dot diagrams. Well, not yet. Let's do ionic bonding. Ions and ionic compounds are held together into 3-dimensional solids called crystal lattices. A lattice energy is the energy and the change in energy that takes place when separated gas ions are packed together to form an ionic solid. So we take a metal ion, and it needs to be as a gas state. So we have a metal ion in a gas state. We have a non-metal in a gas state, an ion, and we're going to pack them together to make a solid. So that's the lattice energy, and that is proportional to Coulomb's law. So the amount of energy is K times Q1 times Q2 over R. So Coulomb's law is used to determine lattice energy for ionic compounds. And the more energy it has, the stronger those bonds, the more ionic character that compound has. Okay. Okay, let's draw the crystal lattice for sodium chloride. So we're going to have sodium ions, and then alternating chlorine ions, and then sodium ions, and then chlorine, and just alternating. And they're all packed together. And we can just make this just big enough to where it's complete but not overkill. And then if you want, you can put a circle around each of these atoms. And there's our structure. And if you wanted to, you could go to each of these chlorine atoms. Each of those chlorine atoms should technically have a full outer shell like that with a -1, but I'm not going to go through and do that. But that would be our picture there. So sodium and chlorine ions alternating. And there's a little attraction there. But we're not going to show bonds because these are weak bonds, so we're not going to show them because if we were to put this in water, it's going to break up anyway. So it's not a permanent bond. It's almost kind of like a temporary bond. I mean, it is permanent, but it's pretty weak. You put this in water, water will come through here and destroy these crystal lattices like a tornado destroys a house. It's going to go through, and the sodium is going to be attracted to the oxygen. The chlorine is going to be attracted to the hydrogen, and we're going to make those hydration spheres that we talked about before, where water will surround one of these ions. You're going to have a chlorine ion, and you'll have the hydrogens like that. And then you'll have hydrogen here, and so on. And so you're going to have all these water molecules come and surround that poor defenseless chlorine ion. All right. Draw the Lewis dot diagram for the sodium for a couple compounds. All right, so let's do these. I'm going to have you guys do these on your own. Look back at the notes that we just did back here to draw the Lewis dot diagrams for these guys. So we did several examples here. Let me find them. Here we go. So here's all the examples here. So this compound diagram at the end is the Lewis dot diagram that we're looking for. So draw the Lewis dot diagrams for those in that example using these examples here. Okay. So let's go back. There we go. So we're gonna draw those as best you can. Okay. If you need help with the formulas, I'll give you the formulas. NaCl. Magnesium fluoride is MgF2. Aluminum oxide is Al2O3. Calcium phosphide. Calcium's a +2. Phosphorus is a -3. So Ca3P2 is the formula for that guy. You guys remember how to cross the charges like that? I hope so. So there's our formulas for those. Covalent bonds, we did that. Electrons are shared between atoms. 2 nonmetals needed for a covalent bond. Beryllium can also make covalent bonds. So Be can actually break the octet rule. It's an exception to the octet rule, and it can share electrons with extremely electronegative atoms like chlorine or fluorine. A double bond is 2 electrons shared. A single bond is 2 electrons shared. A double bond is 4. A triple bond is 6 valence electrons shared. Okay. Lewis dot diagrams. How do we draw them? Determine the total number of valence electrons in the molecule. It must be an even number. There are exceptions, but they're very, very rare. So even number of electrons. We're going to put the least electronegative element in the center if it has a center. If it has a center, the least electronegative element will go in the center. Connect all outer atoms to the centered atom by drawing 2 electrons or a solid line representing the covalent bond between them. Add electrons to the outer elements until all of the elements have an octet. That's supposed to be elements there. Elements. So the outer elements need to have an octet, and then add any remaining electron pairs to the central atom at the end if you have them left over, and if the central atom can still hold more. And we'll talk about that. Some elements can have more than 8. We'll talk about that. So we can break the octet rule. All right, draw the Lewis dot structures for the following. So let's just go through these. Hydrogen is going to be here. Hydrogen has 2 valence electrons. HCl has 8 valence electrons. CH4 has 16. Oxygen has 12. Nitrogen has 10. This one has, let's see, C2H6O. So that's 2 carbons, which is 2 times 4. So that's 8. 6 hydrogens. So that's 6 times 1. That's 6. And then we have 1 oxygen, which is 6. So we add those up. That's 12. That's 20. So 20 valence electrons in this guy. And that's how you add up your electrons, like so. Let's erase that. Let's do our Lewis dot diagram. So H2 looks like that. HCl looks like that. Chlorine's going to have 6 on its own. Again, any of these elements like oxygen, chlorine, fluorine, anytime they have a single bond, they're going to have 6 left over, right? Because if you add those 2, that makes 8. So anytime you have a single bond, those outer elements are going to have 6 dots on them in every one of these compounds. So that's why I'm trying to show you guys these patterns, because these become pretty easy once you get the pattern. Once you pick up on it. Okay. HCl. CH4 looks like this. Carbon's in the middle. Hydrogen's on the outside. We have a total of 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. So there we go. Oxygen we showed you is like this. Again, when you have a double bond, you're going to have 4 electrons on each of them. N2 looks like this with a triple bond and 2 electrons left over. Let's draw the structure of C2H6O. The least electronegative element goes in the center, which would be hydrogen. Alright, but hydrogen cannot go in the center ever. If a molecule has hydrogen, it will not be in the center. Okay? So hydrogen cannot go in the center. So if hydrogen's the least electronegative and it can't go in the center, we're going to look at carbon and oxygen. We're doing this one here. Carbon and oxygen. Oxygen is more electronegative, so carbon will go in the middle. So let's put carbon in the middle. Let me get some room to do this. So here's carbon, and we're actually just going to attach those 2 carbons by a single bond. And then we're going to go ahead and fill in the rest. Kind of like this. We have 6 hydrogens, so the reason we're going to have 4 is because carbon likes to bond with 4 things unless it double bonds. So most of the time carbon will bond with 4 things. So that's why I'm putting a line on each side of it. So that's 1, 2, 3, 4, 5. That's 5 out of the 6 hydrogens. What we have left is an oxygen and a hydrogen, and they're actually going to be over here like this. We're going to have 4 dots left over on that oxygen because we have 2 here and 2 here. So that's 4 shared, and so it's got 4 left. So that is going to be our Lewis dot diagram for, this is actually ethanol, which is what you drink when you drink alcohol. So there's ethanol. Cool. I just wanted to do kind of a harder one. All right. Types of covalent bonds. Non-polar covalent bonds is where electrons are shared equally. So you might want to take a break here. So if you've already done this video in one sitting, I would recommend taking a break before doing this one. So please pause me, take a break, do this another day, and then hit this because this part's going to take a little while. So go ahead and do that, take a break, and then come back to this. I don't want you guys to do all of this video in one go because it is very long. So we're going to talk about covalent bonds in more detail. We're going to look at polarity. So non-polar covalent bonds is where electrons are shared equally between atoms. Okay. Electrons spend equal time around each of the atoms in the compound. So that's kind of what we've been talking about. We've been talking about covalent bonds. It turns out that when you share electrons, sometimes the atoms will share them equally, and we call it non-polar covalent bond, or a non-polar covalent compound. But sometimes electrons are not shared equally. Okay, if you have a 2 atoms not share electrons equally, we call it a polar bond. All right, and it's because it creates poles. It creates a positive and a negative pole, kind of like a magnet, like a north and south pole. In a polar covalent bond, electrons are not shared equally. Electrons spend more time on the electronegative atom, all right, because they're going to pull that electron more so that electron actually spends more time on that atom. And they're going to spend less time on the electronegative element because it has less pull. So it's not going to hold those electrons as tightly. This creates a polar molecule where one side of the molecule has an electron density, has more electron density than the other. Therefore, we have a partial or a temporary charge, which we call a dipole. So let's look at hydrogen and oxygen and water. Here's our Lewis structure. The way that we do this is we look at the Lewis structure first. Once you know the Lewis structure, we can learn some concepts of polarity. All right. So when you have a bond between two atoms, and there's a difference in electronegativity between those two atoms. Hydrogen has a pretty low electronegativity, and oxygen is actually one of the top four. Remember, the top four is Fonkel. And then it decreases as you go down the periodic table, and it decreases to the left. So hydrogen is way over here, oxygen's over here. So hydrogen has much less electronegativity than oxygen. So when you have a bond between these two atoms right here, between the hydrogen and oxygen, notice that all the electrons are on oxygen. So these two electrons that are actually shared between these two, both of those electrons actually spend more time around oxygen. Oxygen's going to hog them. Okay? And so that side of the molecule is going to become slightly negative. So we can draw the delta symbol. That's delta, Greek letter delta, and it's going to be a minus sign. So it's going to be a partial temporary charge. So this is delta, and it means partial charge, which means it's not a full charge like an ion, like a sodium plus 1. Not the same as that. It's a partial charge, and it's temporary. So it's not a permanent thing. So it's a partial charge, meaning that those electrons will spend more time on oxygen, making that part of the molecule temporarily partially negative. And then sometimes the electrons will spend less time on the hydrogen, making this side of the molecule partially positive. And then we have the same thing over here. All right, and so these both have dipoles, and we have a dipole moment. So a dipole is where you have a positive and negative charge on a molecule, and what we do is we just draw an arrow to the side of the molecule that has more electrons. And so we're going to draw to the negative, and then we're going to cross right there to show the positive. So that's positive over here, negative over there, and then we also have one over here. So there's two dipoles in this molecule, each between the bonds. And these are kind of like vectors, all right? I don't know if you guys have seen what a vector is in physics, but if you have two vectors like this, what they are going to do is kind of add together and kind of cancel out a little bit, and they're going to make a something like that. So they're going to create and combine to form a larger vector, a larger dipole. So this is what we call a dipole moment. Basically where, again, the oxygen is going to have a partial negative charge, and the hydrogens are going to be positive. So that's what we call a dipole. Okay. What are some examples of non-polar covalent bonds? Non-polar covalent bonds are typically carbon to hydrogen, like hydrocarbons, because the difference in electronegativity there is not big enough. And we'll talk about electronegativity in a second. Should have had it before this. Carbon, hydrogen, or if you have two of the same element, right? If you have two of the same element, they're going to have the same electronegativity. So N2O2, F2, Cl2, those are all nonpolar because they have the same pull for those electrons. Now, what is polar? Water's polar. Ammonia is polar. H2S is polar. SO2 is polar. And basically, these compounds have bonds in them where we have a big difference in electronegativity. Okay, so these are compounds with polar bonds, and we're going to consider them polar molecules actually because they have lone pair electrons on them. So oxygen actually has two lone pair electrons on it, polar. Nitrogen, NH3, as you guys learned when we did acids, has 2 electrons there, makes it polar. Sulfur has 4 lone pair electrons, polar. Sulfur has 4 electrons, polar. HCl is polar. Look at the Lewis dot diagram. Look at all those electrons on that chlorine, polar. Right? It's partial negative, partial positive, and then a dipole right there. So that means that this side of the molecule is going to be slightly negative. It's going to have a high density of electrons, and over here it's going to be slightly positive. Okay. Polar covalent bonds does include acids. Okay, because those are actually molecular covalent compounds. Acids are, even though they make ions in water. All right, here's electronegativity table. All right, so hydrogen is 2.2. Carbon is 2.58. And basically, this is a number for electronegativity. It goes from 0, essentially 0 down here, 0.7, all the way to almost 4. Fluorine is 4. So remember the top 4. FONCl. And then I don't know who's after chlorine. Probably sulfur. And so it decreases as you go that way and down. So it decreases as you go down. All right. So we're looking at the electronegativity between atoms. And we want to see if there's a big enough difference. It needs to have a difference of greater than 0.4. Essentially is how we do this. So we look at the electronegativity values and we see if it's got an electronegativity difference between the two atoms that's greater than 0.4, almost a half. All right, so let's try some examples. Let me actually get rid of this so that we can see the examples. There we go. Let's try these examples. All right, so HO, hydrogen's 2.2. Oxygen is, let me see if I have these in my notes. Polar covalent bonds. 2.2, and oxygen's 3.44. So that's going to be polar. Nitrogen to hydrogen is polar. So anytime you combine something that's over here, like hydrogen, with something that's over here, like fluorine, chlorine, bromine, oxygen, nitrogen, sulfur, you've got something over here that's pretty positive and something over here that's pretty negative. So that's going to create a polar bond. So this one's polar. HF is polar. HCl is polar. Now carbon to oxygen is also polar. That one's kind of not as great, but still oxygen's up here and carbon is a little bit further. So carbon is a couple elements over from oxygen. So you have carbon, nitrogen, oxygen. Carbon's value is, let's see if I see it here. I don't see it here. Is it 2.58? I can't remember, but this one's polar. This one's also polar. This one's also polar. So these are all polar. What's not polar? So non-polar. Anytime you have the same two elements bonded together, or carbon to hydrogen. That's pretty much it. I mean, there's not many more bonds that are non-polar. Same two atoms attached, or carbon to hydrogen is pretty much the main examples. There might be more, but those are the main ones. All right. For each of the following molecules, show the direction of the bond polarities and indicate which ones have a dipole moment. Okay, so we got HCl, and there's our dipole. Cl2 looks like this, the Lewis structure. So I'm going to write dipole here. So this one has a dipole moment, and that's what it looks like. This one has no dipole, because chlorine and chlorine are the same atoms. SO3, let me see if I have that one drawn, SO3. So a compound can have polar bonds and have dipoles, but it may not have a dipole moment, which means it has a net pull on the electrons. So it means that one part of the molecule is positive, one part of the molecule is negative. So SO3 looks like this. Let me explain what I mean. It has single bonds. We're going to pretend like it has single bonds. I think it might have triple bonds or double bonds or something, but we're going to pretend like it has single bonds. This part of the molecule is negative. This part of the molecule is negative. This part of the molecule is negative. And the inside is positive. Because oxygen is more electronegative than sulfur, and it's just enough. That's actually a polar bond. Sulfur to oxygen. If we look at our electronegativity chart, that's actually just enough. And actually, I need to go back and undelete that picture that I deleted. So what we have here is a dipole from here to here, pulling electrons towards that oxygen. Here's a dipole pulling electrons to oxygen, and here's a dipole pulling electrons to oxygen. So the way to think about this is a tug of war. If you had 3 people pulling in 3 directions, pulling equal amounts, 3 people in 3 directions, pulling equal amounts, what is the net pull on the center? And in this case, it's none. All right, and so there's it cancels out.
Motion detected at the front door.
So it's going to cancel out a little bit, okay? And so if it cancels out, there's no dipole. So this is no dipole moment, which means that this is actually a nonpolar molecule. Nonpolar molecule. Because all of the dipoles cancel out, making it there's not enough change in the center. Okay. CH4. Those are all nonpolar bonds, and so there's no dipole, so that's nonpolar. And there's no dipole. H2S has a dipole, just like water did. You got those 4 electrons on sulfur, so that's a partial negative, partial positive, and so you've got 2 dipoles like this. And think about it, if you had 2 people pulling on a rope, angles like that, what's the net force between it? And it's kind of like that. It's going to be the net direction that they're going to go is, the center's going to go is up that way. So this one has 2 dipoles like that. We can actually draw them smaller. Let's draw them in red. So there's that one, there's that one. But the net dipole is going to be kind of like that. That's going to be the net movement. So if you had 2 people pulling at 2 angles on a person standing there, then where are they going to go over time? They're going to go that way, right? All right, so that's the dipole, and this one has a dipole, and this one's polar. Awesome. All right. Polarity is a temporary partial charge. It's generated on each side of the molecule. This produces what we call a dipole, which is kind of like a magnet. It has a north and south pole. One side of the dipole is partially positive, least electronegative side, and the other side is partially negative. And so here's a picture showing it.
Motion detected at the front door.
I told this thing to do not disturb, but I guess it's not going to do it. Maybe I should unplug it. There we go. Okay, let's see. So there's our dipole showing them. These are pictures that I got online. Order the following bonds by increasing polarity. Okay, so we want to start with nonpolar. So if we're going to do order of increasing polarity, we're going to start with nonpolar over here and all the way to polar over here. And increasing polar, so more and more polar. All right, so we have HH. That will be nonpolar. We're going to say it's less than. Let's see what's going to be superpolar. The superpolar one is going to be HF. Think about how far they are apart from the periodic table. Hydrogen's over here. Fluorine is over here. So hydrogen's about 2.2. And remember, fluorine is the most. It's about 4. And so you can remember Fonkel. So HF is going to be greater than HO, which is going to be greater than HN, which is going to be greater than HCl. So we can kind of order them by that. So the next one is going to be, we can cross out the ones that we've got so far. We've got those 2. OH is pretty polar. CLH is even more polar. SH. So SH is our next one. That's not super polar. It's still polar, but not as much so, because sulfur is not one of the top 4, whereas these others are. So SH is going to be next, and then let's just put commas in between them so it doesn't look so messy. So commas between them. CLH is going to be next, and then OH, and then FH. So that should be our order of polarity. And if we look at the differences here, there's no difference here, so no polarity there. Sulfur is 2.58, and this is 2.2. So I mean that's about 0.4, right? So that's really close to the threshold for polarity. H is 2.2. Chlorine is 3.16. Look at the difference there. That's a big difference. Oxygen is 3.44 compared to 2.2. That's a big difference. And then of course fluorine is 4, oxygen's 2. That's a big difference. So there is our right here in this box. That's our increasing polarity. Okay, last thing here. So nonpolar covalent bonds are bonds that have a very little difference in electronegativity. So you either have the same 2 atoms or you have carbon to hydrogen. That's pretty much the main examples of nonpolar. All right, so far we've been talking about how to characterize the bonds between atoms. Polar or nonpolar, sharing electrons equally or not equally. Okay. This is kind of confusing, but there are some molecules that are polar molecules. They're defined as polar because they have a dipole, even though they don't have polar bonds. Okay, and this is actually kind of rare. And that's kind of interesting. Some molecules are nonpolar molecules, even though most of the bonds in them are polar. And that's actually more common. And the reason for that is because they cancel out. Okay, so let's first look at polar molecules. If a compound has a lone pair of electrons on the central atom, it will be a polar molecule without any exceptions. If there's lone pair electrons on that central atom, it will be a polar molecule. Okay, so kind of like we said, H2S. If you've got those electrons there, it's polar. If you got NH3, and you got that lone pair of electrons there, it's polar. If you got if you have methanol, kind of like the one we drew before with the oxygen to hydrogen, and you got those electrons there, that's polar, right? Because there's electron density there that's negative, and then positive everywhere else, so that's going to create a dipole towards that oxygen, dipole towards that nitrogen, dipole towards that sulfur. Okay. So those are all polar molecules because of the lone pair. And there's actually one molecule that has non-polar bonds, but it is polar, and that is ozone. And I think that's the thing of it. And the reason for it is because the central atom has lone pair electrons on it. So O3 ozone is an example of a molecule where all the bonds are polar, but it is a non-polar molecule, or all the bonds are non-polar because it's oxygen to oxygen, no difference in electronegativity, but it is polar because I think these are double bonds, and so only that central oxygen has they all have lone pairs. Let me actually pull up the Lewis dot diagram for ozone. Lewis dot diagram for ozone. Let's look at that. O3. Oh, it's got a double and a single. Okay. There we go. So it looks like this. So as you can kind of see, this one has a lot of electrons. The other two have less. And so there's going to be a dipole there. It's almost going to be like this one's negative because it's got more electrons, this side's positive. But those bonds between the oxygens are non-polar bonds because they're sharing the electrons equally. But the distribution of the electrons in this molecule, because one side has a double bond, the other side has a single bond, means that there's going to be a dipole like that going to that negative side. So that's just a rare occurrence. And that one's not super important. What's more important is the fact that there are some compounds that are non-polar molecules. This is a lot more common. They are non-polar molecules overall because they're symmetric, even though they have polar bonds. So let's look at CF4. CF4. These bonds are polar because carbon and fluorine have a big difference in electronegativity, right? Each of these has 8 on them to fill its outer shell. Carbon has no dots because it's connected to 4 things. That's 4 pairs. That's 8 electrons, so he's happy. Notice the negatives here. Here's the electrons here, so it's partial negative, partial negative, partial negative, partial negative, and then partially positive on the inside. So what we have here is a dipole right here going to that fluorine. We have a dipole going to that fluorine, a dipole going to that fluorine, and that one as well. Notice it's kind of like tug of war. 4 things pulling on someone in the center with the rope. What happens? Where's he going to go? Nowhere. So they all cancel out, and that makes us nonpolar. Okay, pretty cool. If you have 4 things around an atom, and all those bonds are equally polar, meaning that the carbon is attached to the same atom, then they're going to have the same strength. Now, if I replace one of these with the chlorine, okay, this one is not going to be as polar, and so that's going to be a polar molecule all around because we're going to end up with slightly positive here because it's a little less electronegative, a little less polar on that chlorine, and so these guys are going to have, so it's going to be like, here's our center, we're going to have a little bit of polarity for that one to chlorine, but then we're going to have a larger arrows of polarity for the other 3, and so we're going to have a slightly negative side on this molecule, slightly positive over there. So if you change out one of those fluorines to where they're not identical on all sides, then they're not going to cancel out. Okay, so that's kind of cool. CO2 is another one. Carbon to oxygen is a polar bond, but if you have a molecule like this, then you're going to have 2 dipoles that cancel out, one going that way and one going that way. And so if you have 2 people pulling on a center, here's the center, and you pull them equally, then there's no change, they're going to cancel out. So CO2 is nonpolar, xenon F2 is nonpolar, BF3, here's another example, BF3. Extremely polar bond here, but it's pulling equally in 3 directions. And so what happens? They all cancel out, and it's nonpolar. So that's just kind of interesting. You can have a molecule with polar bonds, all polar bonds, but overall it's nonpolar because of the symmetry of the molecule. They cancel out. Very cool. Okay. Determine if the following molecules are polar or nonpolar. So I'll do this real quick. Polar, polar, nonpolar, 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 SO2, I don't remember, polar, nonpolar, that one, PCl5, let's look at that one, P1, 2, 3, 4, 5, so we're going to spread them out equally into a star. You gotta think about this. So you got a top and a bottom, and then you got 3 in the middle. Something like that. I actually like that. Yeah, like that. And so this one is really cool. This one is a PCl5. The phosphorus is in the middle. All of the ends are chlorine atoms. And what happens is we have a dipole pointing up and down, and that cancels out. So let's just erase it. It cancels out. And then in the middle, we have one there, and one there, and they cancel out. Because again, if you have 3 people pulling on a center like this, and they're equal, then he's not going to go anywhere. They're all going to cancel out. So they all cancel out here. So that's nonpolar, which is very cool. And then this one's nonpolar as well. Same thing if you have 6. Let's draw the 6th one. Sulfurs in the middle. You have a top and a bottom, which are going to be those fluorines. And then you're going to have 4 in the middle, spread out like that. And they're going to cancel out. So if you look at the symmetry of this molecule, it's kind of like that. You got your center. So if you had 4 dipoles, they're all going to cancel out. And then you also have a top and a bottom. And they're going to cancel out. So everything cancels out there, so nonpolar. So H2O is polar, NH3 is polar, CH4 is nonpolar, I3 is nonpolar. I3 is cool. It's 3 iodines attached like this. And it looks like this. This is the Lewis structure for it. It's a linear molecule. And so if you have a linear molecule like this, it's gonna, there's actually no dipoles here because they're all iodine, so that's nonpolar. CO2 is nonpolar. CCl4 is nonpolar. SO2 is polar. SF4 is nonpolar. PCl5 is nonpolar, and SF6 is nonpolar. All right. Okay, next thing to do is talk about exceptions to the octet rule and talk about Vesper theory and resonance. We're actually not going to talk about formal charge because it's not on the AP test, so we'll not do that. So I think I'm done for the day. I'm going to give you guys a link to the simulation where you can practice looking at polarity to kind of get your mind wrapped around it because it's kind of abstract. Thank you guys. Sorry the video was so long. We are almost done here. Y'all have a great one.